This is the same question as before, but I've added another part. What is the force of the ground on the person in the horizontal direction? So now we're interested in the person. If I draw a free body diagram of the person, what are the forces acting on that person? Well, there's gravity. So there's an mg pulling down on the person. The person is not getting sucked down into the ground. They're being held up. So there must be a normal force pushing them up from the ground. They're pushing on the car, and the car may actually be pushing back on the person. Because if the car wasn't there, the person would just fall forward. And since the person isn't falling forward, there must be a force pushing back from the car. So this is an F, I don't know what to call it. I'm going to call it F from the car. So it looks like there's a force going back from the car that direction. Then, if these are the only forces, and this direction cancels out, there would be a net force on the person to the left. So as the person is pushing the car, are they accelerating, being forced backwards? The person would actually have to be accelerating the same as the car, because the person stays touching the car. So if the person's accelerating that direction along with the car, then there must actually be a net force that direction on the person. So the car is pushing back on them. Something else is pushing forward even more. And that has to be coming from the ground. What kind of force is that? So the surface is here. It's not a normal force because that would be this direction. Parallel to the surface has to be a frictional force. So this is a force of friction applied from the ground to the person. And that kind of makes sense. It sounds weird because the friction force is what's actually making them move. Normally friction tries to stop things. But if you think about it in terms of, if I put this on a sheet of ice, and the person was trying to push on the sheet of ice with very little friction, then their feet would be sliding. If they're wearing rubber shoes on cement, then they'll stick well. There's a lot of friction, and that'll make them push more effectively. So it is a force of friction that's actually pushing that person. All right, so what is the force of the ground on the person? That's what this F is. So now we've got an unknown F that we're trying to find. So how do we find that F? Okay, so the person is pushing on the car. The car is apparently pushing back, but we don't know by how much. So in this case, so I don't have to worry about this, I'm actually going to look at a different system. So the car plus person system. Okay? If I consider the system of the car and the person together, draw a free body diagram of that, I'm going to have I have mg. This is now the total mass of the two of them. We've still got a normal force pushing up from the ground. So the normal force and mg, and what about forces in this direction? We had the applied force here, but that was coming from the person. The person is now part of the system. And when you define a system, you don't care what the forces are inside the system. You only care about the things that act on that system. Just like for holding the book up, I didn't care about what are the forces, is there glue holding the pages together here on the binding? I don't care about any of the forces inside the book. I care about what's acting on the book. So with the car and the person as my whole system, I don't care what the force is inside. I only care about what acts from outside. So normal force is acting on them. Gravitational force is acting on them. And the only other force is this frictional force from the ground. So now my free body diagram is simpler. I know whatever that friction force is from the ground, that's pushing those two. Okay? Now I can use sum of forces equals ma, right? We're going to consider only the x direction. So the sum of forces in the x direction equals ma. I know what the acceleration is. And this acceleration is good for both the person and the car. So this is the mass of the system, 70 plus 700, so 770 kilograms, times the acceleration of the system, 0.286 meters per second squared. So I know that the net force in the x direction, so if I put the x directions here, I can take the vectors off. So net force in the x direction, that's this F, is 220 newtons. So the force from the ground on the person, which is what this was asking for, that's the force here. It's the same as this force, 220 newtons.